In 1972, a 24-year-old graduate student at Princeton could not sleep, and it was his advisor's fault. The student's name was Jacob Bekenstein. The advisor was John Wheeler, the man who had given black holes their name, a physicist with a gift for asking the kind of small, quiet question that takes the floor out from under an entire field. And one afternoon, almost in passing, over the ordinary murmur of an office conversation, Wheeler asked Bekenstein something that should not have been frightening at all. He said, "What happens when you pour a hot cup of tea into a black hole?" It sounds like a joke. It is not a joke. Because a hot cup of tea is a little parcel of disorder. The molecules in it are jostling, random, chaotic, and physicists have a number that measures exactly how much disorder is in there. They call it entropy. And there is a law, maybe the most ironclad law in all of physics, the second law of thermodynamics, that says the total entropy of the universe can never go down. Disorder always wins. Always, you can clean your room, but only by burning energy and dumping more disorder into the air than you removed from the floor. The universe never lets you erase the mess. It only lets you move it. So Wheeler smiles and asks his student, what happens when you take that cup of disorder and drop it past the event horizon of a black hole, into the one place in the universe nothing can ever come back out of? The tea is gone. The entropy it carried is gone with it. And the universe, it would seem, just got a little more orderly. You have just broken the most unbreakable law in physics, and you did it with a teacup. You could erase every trace of disorder in the cosmos, one cup at a time, by feeding it all to the dark. Bekenstein went home, and he could not let it go. And when he came back, he had an answer so strange that the most powerful minds in his field told him, more or less to his face, that he had embarrassed himself. The answer was this: the entropy is not destroyed. It cannot be. So the black hole itself must carry it. The black hole must have an entropy of its own. And when you feed it the tea, its entropy goes up by at least as much as the teas went down. The books stay balanced. The law survives. But that was only the first half of the idea. And the first half was not the dangerous part. The dangerous part was where that entropy lives. Because Bekenstein worked out that a black hole's entropy is not proportional to its volume, to how much room there is inside it. It is proportional to its area, to the size of its surface, to that two-dimensional membrane we call the horizon. Everything that ever fell in, every cup of tea, every star, every encyclopedia, every person, all of the information about all of it, is somehow accounted for not by the vast space inside, but by the thin skin stretched around the outside. And I know how that sounds. It sounds like a technical detail about an exotic object none of us will ever go near. But hold on to it, because that single sentence, area instead of volume, surface instead of inside, is going to come back around, and it is not going to stop at black holes. It is going to arrive at the chair you are sitting in and the hand you are reading this with, and it is going to ask both of them a question they may not survive. I want to make you a promise before we go any further, the same way I think Bekenstein deserved to be warned. What I am about to walk you into is not fringe. It is not a stoner's late-night theory or a YouTube fever dream. The road from that teacup leads, step by step, through some of the most decorated minds of the last 50 years. A Nobel laureate, the most cited paper in the history of theoretical physics. Men who did not want this to be true, who fought it, one of whom spent the better part of a decade trying to prove it wrong and accidentally proved it right instead. By the end of this, you are going to understand why they surrendered, and you are going to understand why the surface of a black hole and the surface of your own existence might turn out to be the same kind of thing. So let me ask you Wheeler's question, but point it at you instead of a teacup. Right now, there is a certain amount of information that it takes to describe you completely. Not just your name and your face, everything. The position and motion of every atom in your body, every electron and every nerve, the exact firing pattern of the neuron that is reading this word at this instant. There is a number, an unimaginably large but finite number, of yes or no answers, of bits, that would capture the entire physical truth of you in this moment, with nothing left out. And here is the only question that matters for the next 40 minutes. Where does that number live? Is it stored in the volume of you, spread through the three-dimensional meat and bone and water? Or is it written somewhere else, on some surface you cannot see, and the inside of you? The very thing you feel most certain about, the sense that you are a solid thing with a depth and an interior, is the part that was added later? To get there, we have to go back to the horizon, because the horizon is where physics first noticed that depth might be a lie. When Bekenstein said a black hole has entropy, he was not just bending the second law back into shape. He was committing himself to something far more disturbing, because in physics, entropy and temperature are joined at the hip. If a thing has entropy, it has a temperature. And if it has a temperature, it glows. Everything with a temperature radiates. The embers of a fire, the filament of a bulb, your own skin pouring out infrared into the room around you right now. So Bekenstein's idea carried a hidden claim inside it like a splinter. Black holes must glow. And that was a step too far, even for the people sympathetic to him, because the entire definition of a black hole is that nothing escapes it. Light goes in and never comes out. A glowing black hole is a contradiction in terms. It is like saying a hole in the ground is actually a fountain. So when a young British physicist named Stephen Hawking heard about Bekenstein's entropy, he did not believe it. He thought it was wrong, and he set out to do what physicists do to ideas they think are wrong. He set out to demolish it with mathematics. He failed. He failed in the most spectacular and famous way it is possible to fail in science. Because when Hawking applied the rules of quantum mechanics to the empty space right at the edge of a black hole, the equations told him something he did not want to hear. They told him the black hole was warm. They told him it radiated. A faint, ghostly hiss of particles leaking out of the horizon, carrying energy away, very slowly bleeding the black hole dry. The mechanism, when you finally see it, is almost worse than the conclusion. Empty space, the vacuum, is not actually empty. Down at the quantum scale it churns, constantly throwing up pairs of particles, one matter, one antimatter, that flicker into being and annihilate each other so fast that the universe never has to pay for them. They are a loan the vacuum takes out and repays in the same instant. But right at the lip of a black hole, the loan goes bad. One of the pair falls across the horizon before the two can find each other again, and its partner, suddenly orphaned, with nothing left to annihilate against, is forced to become real and drifts away into space as radiation. The black hole pays the debt out of its own mass. Particle by particle, orphan by orphan, over a stretch of time that makes the present age of the universe look like a single tick, it pays itself out of existence. We call it Hawking radiation now, and it confirmed Bekenstein down to the decimal point. The man who tried to kill the idea ended up signing his name to it. Today, the formula for a black hole's entropy carries both their names, Bekenstein and Hawking, the skeptic and the student, bound together forever by a number neither of them wanted. And that number is the most important thing I will show you tonight, so let me show it to you plainly. No equations on the screen, just the meaning of it. Take a black hole. Look at the area of its horizon, that two-dimensional surface. Now imagine tiling that surface with the smallest tiles the universe permits. Tiles so small, they make an atom look like a continent. Tiles measured in something called the Planck length, the scale at which space itself stops being smooth. Count the tiles. Divide by 4. That number, the number of tiny tiles it takes to cover the surface, is the entropy of the black hole. It is, in the deepest sense physics has, the amount of information the black hole can hold. The maximum number of bits you could ever cram into that region of space. Sit with what that means, because it is genuinely strange. The information capacity of a region is not set by its volume, it is set by its area. A black hole the size of a city does not store information like a warehouse, where you would think a bigger inside means more room for stuff. It stores it like a sheet of paper, where all that matters is the surface. And the inside, all that volume, all that depth, is not where the books are kept. Let me press on how upside down that is, because your intuition is going to try to wave it away, and your intuition is exactly the thing that cannot be trusted here. Everywhere else in your life, capacity scales with volume. A bigger box holds more. A bigger drive stores more. Double the room and you double the space for things. If I told you a warehouse could only ever hold as many crates as you could paint onto its outer walls, no matter how cavernous it was inside, you would think I had lost my mind. And yet that is precisely, mathematically, the rule the universe enforces at the limit. When you try to pack more and more information into a region, you do not fill it like a box. You approach a black hole. And the amount you can store before the whole region collapses into one is set, always, by the surface. It is as if reality has a maximum resolution, a finest possible grain, and that grain is spread across surfaces not packed through volumes. The three-dimensional fullness we take for granted, the feeling that space has room inside it, turns out to be the cheap illusion. The expensive truth, the real ledger, is kept on the skin of things. Now you might think, fine, that is a fact about black holes, and black holes are monsters, the most extreme objects in existence, so maybe they just play by their own broken rules. But here is where it stops being about black holes. Bekenstein realized you could turn the whole thing into a universal law, and physicists now call it the Bekenstein bound. It says this: take any region of space at all, any region, the space inside this room, the space inside your skull. There is a maximum amount of information you can ever fit inside it, and that maximum is set by the area of the boundary around it, not by the volume within. And the way you reach that absolute maximum, the most information you could ever pack into a given space, is to collapse it into a black hole. A black hole is not a place where information goes to die. A black hole is the most efficient hard drive the universe is capable of building. It is what a region of space looks like when it is completely full. So if you wanted to store the maximum possible information about everything in this room, you would not need a computer the size of the room. You would need, in principle, a record on the surface of the room. The walls would be enough. The inside would be redundant. This whole channel really only exists because enough people decided not to look away from sentences like that one. Because the honest response to all of this is to feel your stomach tighten slightly and want to change the subject. And most people do. But if your stomach is tightening and you want to keep going anyway, if this is the kind of rabbit hole you would rather fall all the way down than back away from, then stick around, because where we go from here is stranger than the black hole was. The black hole was just the place we first noticed the pattern. Now we follow the pattern home. But before we follow it to the man who named the idea, we have to sit inside the wound that Hawking's accidental fire tore open. Because the wound is the whole reason the holographic idea had to be invented. Remember what Hawking found. Black holes radiate. They leak. Slowly, across spans of time that dwarf everything, a black hole bleeds itself away into that faint hiss of particles until, at the very end, it is gone. Evaporated. And here is the problem that took the best part of 30 years and very nearly tore theoretical physics in half. When the black hole is gone, where did the information go? Think about what fell in. Encyclopedias, stars, the tea, a person, anything at all. Each of those things carried an enormous specific quantity of information, the exact arrangement of all its parts. And quantum mechanics has a rule about that information, and the rule is not a suggestion. It is the bedrock the entire theory is poured on. Information is never destroyed. The present always contains, in principle, a complete record of the past. Burn a book and the information is not gone. It is scrambled, smeared into the smoke and the ash and the heat and the light, in principle recoverable if you were patient and clever enough to gather every photon and every particle of soot and run the film backward. Nothing is ever truly erased. That is the law underneath all the other laws. But Hawking's radiation seemed to break it, because the particles leaking out of a black hole, by his own first calculation, were random. Featureless, thermal, they carried no memory of what had fallen in. A black hole that swallowed a library, and a black hole that swallowed an equal weight of poison wood on their deathbeds, radiate exactly the same meaningless static, and then vanish. The information did not come back out with the radiation. And it could not have stayed inside, because there is no inside anymore. The inside is gone. So it was destroyed. Erased, deleted from the universe completely. For most people, that would be a footnote. For physicists, it was a 5-alarm emergency. Because if information can be destroyed even once, even at the bottom of a black hole, then the law that forbids it is false, and if that law is false, then the entire structure of quantum mechanics, the most successful theory in the history of science, the thing your phone and your body and every atom quietly depend on, is built on sand. Hawking believed the information was gone. He said so for years, and he meant it. And against him stood Leonard Susskind and Gerard Hooft, the same two men we are about to follow into the hologram, who insisted the information had to survive, that quantum mechanics simply could not be wrong about something this fundamental, that there had to be a way out. It became, in Susskind's own words, a war. It ran for the better part of 2 decades. In 1997, it even hardened into a literal bet, Hawking and the relativist Kip Thorne wagering against a physicist named John Preskill over whether the information was truly lost. And the way the war finally ended, the only way it could end, is the thing that should put the hair up on your arms, because it is the hologram arriving early, before anyone was ready to say its name out loud. The resolution is that the information was never inside the black hole to be destroyed in the first place. It was on the horizon the entire time. Smeared across that 2-dimensional surface, the same surface that carries the entropy, encoded into the precise way the radiation leaks out, subtly, correlation by correlation, so that an infinitely patient observer could in principle read the entire history of everything that ever fell in off of the light that comes back out. The inside was never where the truth was kept. The surface was. In 2004, Stephen Hawking stood up at a conference in Dublin and conceded the bet. He had been wrong. Information is not destroyed. It lives on the boundary. And once you have accepted that the complete truth of everything inside a black hole is really written on its surface, you have already said yes to the holographic principle without noticing you said it. All that was left was for someone to ask the obvious, unbearable next question. In 1993, a Dutch physicist named Gerard Hooft asked it. Hooft is not a fringe figure. A few years after this, he would win the Nobel Prize. And he asked the thing nobody wanted to say out loud: if the maximum information in any region is written on its boundary, then what is the inside even for? What if the 3-dimensional world, the world with depth, the world you were convinced you live inside of, is not the fundamental thing at all? What if the real description of reality, the complete one, the one with nothing missing, lives on a distant 2-dimensional surface, and everything we call depth, everything we call volume, everything we call inside, is a kind of image projected up out of that surface? He gave it a name: He called it the holographic principle, and he chose that word with terrible precision, because a hologram is exactly this trick. A hologram is a flat piece of film, two-dimensional, with no depth in it at all, just a pattern of fine scratches and interference. And yet, when you shine the right light through it, a three-dimensional image floats up into the air. An image with a front and a back and sides, an image you could walk around if it were big enough, an image that has every appearance of depth. But the depth is not in the film. The depth is in the encounter between the flat film and the light. The film is flat. The depth is the show. 2 years later, a physicist at Stanford named Leonard Susskind took the idea and made it concrete and unflinching. In a paper he titled, with no hedging whatsoever, "The World as a Hologram." Susskind is one of the founders of string theory, a man not remotely given to mysticism, and he wrote it down flatly. The three-dimensional world of ordinary experience, he said, may be an image of reality coded on a distant two-dimensional surface. If you have ever held one of those holographic stickers, the kind they put on a credit card, and tilted it back and forth and watched a little three-dimensional shape swim and shift inside a film you know perfectly well is flat, then you have held this entire idea in your hand and not realized it. There is no depth in that sticker. You could put it under a microscope and find nothing but a flat, scratched surface, a frozen pattern of interference with no front and no back anywhere in it. The three-dimensionality you see is manufactured, completely, by the way light scatters off that flat code and into your eye. Now perform the thought that Hooft and Susskind were performing. Imagine the image in the sticker were rich enough to contain a tiny person. And imagine that person could think. That person would look around at their little holographic world and find it utterly, convincingly three-dimensional. They would see depth in every direction. They would feel they had an inside. They would be able to prove, by every test available to them from within the image, that they lived in a volume. And they would be wrong, and there would be no way from inside for them ever to find out. That person is us, in this story. The flat sticker is the boundary of the universe, and the light doing the projecting is the laws of physics themselves. And now I have to be honest with you about the state of the idea at this point. Because, if I am not, you should not trust me with the rest. As of 1995, this was a hunch. A beautiful, terrifying, well-motivated hunch, resting on the black hole entropy that Bekenstein and Hawking had genuinely proven, but a hunch all the same. Yet Hooft and Susskind were saying the universe should work this way. They could not yet show that it did. They had the suspicion. They did not have the proof. The proof came in 1997, and it came from a quiet 30-year-old Argentine physicist named Juan Maldacena. And the reason you have probably never heard his name, even though what he did is arguably the most important single result in theoretical physics in the last half-century, is that what he proved is almost impossible to make sound as enormous as it actually is. His paper became the most cited paper in the entire history of the field. Thousands upon thousands of physicists built the next 20 years of their careers on top of it. And what he showed was this. He took a particular kind of universe, a universe with gravity in it, a universe with a three-dimensional bulk, an inside, depth, the works. And he took the two-dimensional surface that wraps around that universe, and he wrote down, with full mathematical rigor, a precise dictionary between them. He showed that the gravity in the three-dimensional interior and a completely separate quantum theory living on the two-dimensional boundary, a theory with no gravity in it at all and no depth anywhere, are not two related things. They are not analogies for one another. They are the same thing. Every event in the deep interior, every particle, every force, every collision, corresponds exactly to something happening on the flat boundary, and the other way around, with nothing left over, nothing lost in translation. Two descriptions of one reality. One of them has an inside, the other one does not, and they are equally true. they contain precisely the same information. They are, in the only sense physics recognizes, identical. Let me make that less abstract, because abstract is how an idea this size hides from you. In Maldaceno's dictionary, a single particle drifting deep in the three-dimensional interior is not represented on the boundary by a single particle. It is represented by a whole pattern, a coordinated ripple involving enormous numbers of particles spread out across the flat surface, all moving together. When the particle falls deeper toward the center of the interior, the ripple on the surface spreads wider and grows fainter. When two particles collide and scatter in the depths, the surface answers with a choreography of its own, a storm of correlations that contains every detail of the collision, the angles, the energies, all of it, without anything ever moving in a third dimension. Because on the surface, there is no third dimension to move in. Depth, in the dictionary, is not a place. Depth is a pattern. The distance into the interior is just a measure of how spread out and how gentle the matching ripple on the surface has become. The bulk is the boundary, retold in a language that happens to look like space. This is the equation at the edge of the black hole. This is the one I promised you in the title. Maldaceno's correspondence is, in the most literal way available to mathematics, a proof that a universe with depth can be written down perfectly as a flat sheet of information with no depth in it. The inside is not necessary. The inside is one way of telling a story whose other version fits entirely on the surface. And once a thing has been shown to be possible, once the math actually closes, the question is no longer can reality be a hologram. The question becomes the one you have been dreading since the teacup. Is yours? Now, you might stop me right here. You might say fine, but you are cheating, and I caught you. Maldaceno did not prove it for our universe. He proved it for a toy. The universe he used, the one with the clean boundary you can wrap a theory around, is a special kind of space physicists call anti-de Sitter space. A cosmos curved in a way that makes the math behave. A cosmos with a wall around it. And our universe is not like that. Our universe is flat, or near enough, and it is expanding, accelerating, flying apart with no wall anywhere in sight. So you have shown me that a hologram is possible in a fantasy cosmos that is not the one I live in. You have proven something about a snow globe and told me it is about the sky. And you would be right to push, because that is exactly the honest objection, and it is the very one working physicists still argue over today. So let me give you the honest answer, which is more unsettling than a clean victory would be. Yes, the airtight proof lives in the toy. That is what toys are for in physics. They are the places where the math is clean enough that you can actually see what is happening. The laboratory where you can hold the idea still and confirm it is real. But the thing that started this whole avalanche, Bekenstein's bound, the law that information is capped by area and never by volume, did not come from the toy. It came from black holes. And black holes are not a fantasy. They are out there, billions of them, and the one at the center of our own galaxy has been photographed. That bound holds in our universe. It has survived every single test anyone has been able to throw at it for 50 years. The holographic principle is the suspicion that the bound forces on you. The toy universe is only the one place we have so far managed to write that suspicion down as a theorem. The principle leaks out everywhere we look. We simply have not yet built the version of the math that fits our particular sky, and a growing number of very serious people believe that is a matter of time, not of truth. And there is one more name you should be handed here, because it is the bridge across exactly the gap you just caught me at. In 1999, a physicist named Raphael Bousso, who had trained under Hawking, took Bekenstein's bound and rebuilt it from the ground up, so that it would work not just in the toy, not just around a tidy black hole, but in a real, dynamic, expanding universe like ours. He called it the covariant entropy bound, and it is one of the very few statements in this whole story that applies, as far as anyone can tell, to the actual cosmos you are sitting in right now. It says, in its careful way, the same brutal thing: the information contained in any chunk of the world is limited by a surface, not by a volume. Busso's Bound does not need the snow globe. It holds out here, under the real, accelerating sky. It is the holographic principle stripped of the toy and written in a language our own universe speaks. And it has not been broken. So when I say the surface, not the inside, I am no longer only talking about a black hole or a fantasy space-time. I am talking, by every indication we currently have, about here. About this room. About the boundary you could draw, right now, around your own body. So set the toy aside, and come back to the thing the toy was only ever pointing at, because I do not want you to leave here thinking this is a quarrel about exotic space-times. I want you to feel where it lands. It lands on you. Think again about that finite number, the total information it would take to specify you completely, every atom, every charge, every flicker of thought. The holographic principle says that number is bounded by your surface, not your volume. And I want you to resist the urge to file this under metaphor, because it is not a metaphor, it is an accounting. Run the count on yourself. The number of bits it takes to specify a human body completely is large beyond intuition, but it is finite, and the principle puts a hard ceiling on it, and that ceiling is an area. Draw a sphere around yourself, just large enough to hold you. Tile its surface in those impossibly small plank tiles. Count them, divide by 4, and you have the absolute maximum amount of information that could ever describe you and everything inside that sphere, down to the last quantum detail. And the staggering thing, the thing physicists checked and rechecked because they could not believe it, is that this surface number is more than enough. There is room on the boundary of you to write down all of you, with nothing left over and nothing left out. The inside is not carrying information the surface could not hold. The inside is not pulling its weight. By the only measure physics has, the inside of you is redundant. Everything that you are could be said, in full, on your edge. John Wheeler, the man who started all of this with a cup of tea, spent the last years of his life chasing a phrase he hoped would capture it. He called it from bit. The idea that everything physical, every particle, every field, every it in the universe derives in the end from information, from answers to yes or no questions, from bits, that the substance we take to be fundamental, the stuff, the matter, the solidity, is the secondary thing, and the information is primary. The hologram makes that phrase exact. The bits live on the surface. The it, the apparent stuff with its apparent depth, is what the bits look like when you are standing inside the projection and you mistake the image for its source. And it does not stop at your body, because the same law that caps the information inside a sphere around you caps the information inside the largest sphere there is. Our entire observable universe is wrapped in a horizon, the farthest distance light has had time to cross since the beginning. That horizon has an area. Tile it, divide by 4, and you get a number, a specific, finite number, the total information content of everything we can ever see, every galaxy, every star, every person who has ever lived, the whole observable cosmos. And that number, too, is set by the surface, by the area of the sky, and not by the unthinkable volume it encloses. The universe itself, in this telling, is the projection. The boundary is the film. And you are not even a single pixel in the image. You are a faint, local thickening in a pattern of information painted on the inside of the sky. And the cruelest part, the part that should keep you up the way the teacup kept Bekenstein up, is that there is no experiment you could ever run from inside the hologram to feel the difference. The projected image of a person would feel exactly as solid, exactly as deep, exactly as three-dimensional as you feel right now. It would reach out and touch a wall and feel the resistance. It would look down at its hands and see depth. It would be utterly, unshakably convinced that it lives in a volume, that it has an inside, that the world has a genuine thickness to it. It would feel precisely what you are feeling at this moment, because what you are feeling at this moment is the only thing the projection ever feels. The surface does not know it is a surface. That is the whole trick. That is what makes it a hologram and not merely a picture. The image is convinced of its own depth. You already know what it is like to live inside a convincing projection, by the way. You do it every night. In a dream, you move through rooms with depth. You walk down streets that recede away into the distance. You pick up objects and feel their weight. And at no point, while it is happening, does any part of you suspect that the entire three-dimensional world around you is being generated by a flat sheet of firing neurons that contains no rooms and no streets and no distance anywhere inside it. The depth of the dream is total. It is completely manufactured, and you never catch it, not once, until you wake. The holographic principle is the suggestion that waking life is the same kind of trick, run on a vastly larger and more rigorous machine with a single difference that quietly removes the one comfort the dream still leaves you. From the dream, you wake. From this, there is no surface to wake up onto, because the surface is where you already are. There is no inside to return to. The projection is the only address you have ever had. So here is where the teacup finally arrives, 50 years and 3 or 4 geniuses later, at the chair you are sitting in. You feel three-dimensional. You feel like you have an inside, a private interior volume where the real you is kept, somewhere behind your eyes, down in the dark, warm center of your skull. It is the most immediate fact of your existence. It is more obvious than any equation, more certain than anything a physicist could ever tell you. And yet the most rigorous physics human beings have ever produced, the line that runs unbroken from Bekenstein's Sleepless Nights, through Hawking's Accidental Fire, through 't Hooft's Nobel, and Maldaceno's Proof, and Busso's Bound, keeps arriving, reluctantly, against its own stated wishes, at the same quiet and devastating possibility that the complete and total truth of you, with absolutely nothing left out, may already be written, in full, on a surface you will never see and can never reach. A surface that has no inside at all, and that the depth you are so sure of, the inside you would swear your life on, is the one thing in the entire description that was never really there. Look down at your hand. Feel how solid it is, how it has a front and a back, how the bones sit somewhere in the middle of all that flesh. Ask yourself, honestly, where that middle actually is. Then notice that you cannot find it. Old, fade,